What do you see now? Good. Which chapter is it? Good. Okay. What do you see now? Good. Thank you for checking with me. Thank you very much. Okay，我個即係開咗 recording。I've been trying to switch over different application. It seems it's all right. Hello? What can you see from the blackboard? Hello? Yeah. Okay, good. Okay, this is our second online session for this course. Could you hear my voice? Say yes, please. Okay. Could you see the screen? What's the topic? Could you tell me the name? Yes. Okay, that's good. Now, before we are going into the chapters. First of all, I have to tell you about the student learn hours. Now, is the hour we expect or the college expect you to spend how many hours for each individual activities? Say for lecture, we expect you for 2 hour lecture, you have spent 1 hour for the preparation work. In other words, you have to download the lecture notes and go through the lecture notes, okay, and attend the 2 hour lecture. So you have to spend 3 hours for lecture. Now for 1 hour tutorial session, we expect you to spend additional 3 hours to complete the tutorial assignment, okay? Whether it should be submitted to me or there is no requirement for the submission. Anyway, for each tutorial, you have to spend a total of 4 hours. And then you have to spend 2 hours more for your self-study, right? Whether you are going to search the material from the web or to discuss with your classmates and so on, right? Self-study, 2 hours, okay? So that is the expected learning hours from us, right? We are expecting you to spend all these learning hours, okay? Okay, we'll start now our lecture on the effective stress. Now, this is the remaining part of the chapter 2. Effective stress in Chinese, 有效應力. Now, it's a very important concept in soil mechanics. It's a milestone development in the soil mechanics that we have this concept, effective stress. Now, what's the effective stress? Imagine you got a soil particle, okay? Now it weighs 1.5 kilogram in air. If you put the whole thing, right, the whole arrangement into a tank of water, it weighs less. So if its weight in air is 15 kilogram or 1.5 kilogram, and then if it weighs in water, it weighs less. So that is the very basic understanding of science, right? Because of the flotation, because water is there, so it weighs less in water. For the same concept, we also define effective stress in the soil by this analogy. Okay, the similar principles, right? So the stress exists between the soil particle will be equals to the total stress minus the pore water pressure. So it looks a very similar weight with that the soil immersed underwater. So that's the effective stress equal to the total stress minus hydrostatic water pressure. Now look at this diagram. P is the total weight, okay, the total stress. And then you can see the U here. You can see the U here, right? The U here. Now this U, the pore water pressure, tend to separate the two particles away because of this pore water pressure. It pushes the two particles a bit away, right? So leaving so the total stress because of this upward force, it becomes what? This effective stress smaller, right? For instance, the P is 50 and the push is 20. So the actual stress being in contact will be what? 50 minus 20 equals to 30, right? So the effective stress is equal to P minus U, right? So in other words, 50 minus 20 equals 30, right? So that's the concept of the effective stress. Now, if you use this equation, the total load is equal to so P is the total load. So P is the total load, right? And it's equal to the effective stress plus the water flux or forced. Flux is equal to area times the pore water pressure. Right? U is the pore water pressure. Right? Pressure times area is equal to force. Now, what's the area? So you can see so the area of contact between the soil contact. AC is the C for contact. So the area of contact is very small, right? Compared with the water area. So the AC will be much smaller than the total area. So if you divide this equation further by the total area, so you got this, but here AC much smaller than A, so AC over A will be almost equal to 0, right? So the sigma equals the effective stress plus U, or sigma dash equal to total stress minus U. So this equation has been confirmed, right? A here. Zero. So we have got this very important equation. Effective stress equals to total stress minus pore water pressure. The water in the soil is always kept within the pores, right? In the voids. Okay. So remember that effective stress is equal to total stress minus pore water pressure. So that's end up our chapter 2. Okay. Before we go into the chapter 3, I would like to know and the question for the chapter 2. Well, it has been just uploaded to the Blackboard. I think you can find them from the Blackboard, right? Under the uh, voiceover power presentation. Does anyone have got this PowerPoint from the Blackboard? Under the voiceover PowerPoint presentation, you should have got chapter 2 and chapter 3. Okay, I think I will check it out. Please check over the blackboard tomorrow, right? Whether the new chapter 2 will be available or not. Okay. Okay, now we are going into the chapter 3, the shear strength of soil. Can you see the topic, the PowerPoint, chapter 3? Yes or no? I want to make sure everyone have seen this PowerPoint. Okay. Shear strength of soil. At the end of this chapter, you should be able to quantify the basic shear strength of soils. And you should be able to calculate the shear strength of soil using the Mohr's Coulomb theory, which you have learned about in your structure 1. And finally, you should be able to determine the in situ shear strength of soil. In other words, not only the shear strength of soil in laboratory, but also in a construction site. Now, shear strength of soil, soil shear strength. Right? Now, from the slide, you can see there's a great mass of soil. It's sliding down a slope, right? You can notice that you can see here, right? The shear plane. Here, there's a curved line here, along which the soil mass will be moving down, while the lower part will remain there, right? So the shear plane is not a flat plane. It could be a circular plane. It's not a linear plane, right? It's a circular plane or even of some particular shape. So the geotechnical engineer or the soil engineer are investigating now what is the strength of the soil along this failure plane. We've learned a lot about how the steel bar will fail in tension, and also the concrete will fail in compression. But for soil, the failure could occur by shearing. Okay, so it's a soil. Right? If is going down and this going up. So you got so a pair of shear stress acting along the plane. So remember that, okay? There should be a pair of the shear stresses acting along the plane. So that is the typical mechanical behavior of the soil. Now, why does the soil have that kind of behavior? It's very different from that of the steel and the concrete. It's because concrete and steel are very uniform material or sometimes homogeneous material. But soil is made up of what? Soil grains, right? Soil particles. And sometimes there's the air voids in between. And also sometimes some moisture is kept within that space, right? In the voids of the soil particle. In other words, soil is a mixture of solid, gas, and water. So it's a very complicated material. And this type of material will always fail by shear, just like many granular material. Right? So we are worrying about the sliding down of a very large, massive soil, like a slope. So we are talking about the slope stability and also the foundation failure and so on. Now, the stresses acting along a shear plane always consists of a normal stress and a shear stress. So if you go back to that slide, right? So consider here a soil element there. There's a slope, right? So you got this element, right? You have the vertical stress, sigma 1, and sigma 2, sigma 2, right? Now, if the slope fails, what will happen? So this element, you have the sigma 1, right? And that you have the sigma 2. Now, what happens here, right? According to the Mohr circle, so there's the sigma n. Now that is the normal stress, right? And here, right, you got what? Shear stress. According to the equilibrium, right? The equilibrium of these particles, right? if the element is subjected to the vertical stress sigma 1 and the horizontal stress sigma 2, now acting along this plane, right? Plane, there will be a normal stress sigma n and shear stress, right? Tau. So can you work out sigma n and tau in terms of sigma 1 and sigma 2, right? Very simply by Mohr circle, right? So that's why uh, you got this equation, right? Sigma n is equal to sigma 1 plus sigma 3 or sigma 2 over 2 plus sigma 1 minus sigma 3 over 2 cosine 2 theta. Now, here is the 2D, right? Here, this 2D. So this is a plane element because this element appears on the whiteboard only, okay? It's a two-dimensional element. But in fact, below the ground surface, right? Below the ground surface, you got three dimension, right? X, Y, and Z. So that is say X, Y, and here you got Z, right? So you got the three-dimensional element here. So in other words, in reality, anything below the ground level, every element should be a three-dimensional element. Of course, the mathematical equation is much more complex than the two dimension. Now, the shear strength of soil consists of two parts. First of all, we are talking about friction. Now, what does that mean? Friction. Now, what's friction? Imagine this particle and this particle. Because of the upper part of, sorry, because of the overburden weight, right? Say this soil particle is a very deep, right, below the ground level. Here's the ground level. So you have very deep depth, is that right? So this normal force, sigma normal force, right, is very heavy. So these two particles are simply compressing each other. Right? Now, if you want to move, right, in this way, if you want going to move it, what will happen? You have to overcome the friction, right? Here's the friction. Now, in very basic mechanics, we know friction is equal to what? Mu times the normal force, right? Sigma n is the normal stress. It's the stress you are compressing the two soil particles each other. If you multiply this normal stress with the friction coefficient, you got the friction. So that is the friction, F. So F equal to mu times sigma n, okay? But mu is a friction coefficient, and we want to use this tangent phi to represent the mu, right? Represent the mu. That is the friction angle, angle of internal friction. So this is the first part. Remember, when you are going to slide a layer of soil over the other layer of soil, you have to overcome the friction in between. Well, this friction will depend on how heavy the stress, the normal stress, you compress upon these two layers. The greater the normal stress passing these two layers, you have to overcome a bigger friction force. Okay, so that is the friction of the soil particles. And the friction could be represented by a important characteristic, tangent phi. Phi is the angle of internal friction. Okay, we'll come to that later. Now, we come to this Mohr circle. Now, here, you got, say, that is the, the x direction, and that's y direction. Okay. Now, here, you got what? The shear is equal to 0, right? Tau equal to 0, right? Tau equal to 0. So for this plane, right? For this plane, you got this point. You got this point, right? Because sigma 3 dash 0, right? And then you have here, right? You got what? Here, you got sigma 1 dash 0, right? So you got these 2 points. So you can draw the Mohr circle with the center here, right? You draw the Mohr circle. So the Mohr circle here represent the stress element here, right? We'll learn about that. Mohr's Coulomb strength envelope. We have talked about friction is part of the strength of the soil, the shear strength of soil. In fact, sorry, C plus sigma tangent phi. Now we are talking about this is the friction, right? Because soil particles are always are angular in the shape, so the angular particles will have the friction. Now that's the other part, C. The shear strength of soil. S consists of two parts. We have talked about the friction. Now there's the other part, the cohesion. The soil particles, cohesion of soil. Now what's that? Suppose these two particles here, you want to separate these two things apart, but they are sticking each other. Two particles are sticking each other, like sticky rice, 糯米飯. Okay, so they are sticking together. So you have to apply a force here, right? The force should overcome the internal cohesion of the two particles before they are separate. So if you want to separate the two particles, you have to overcome the internal cohesion. So there's a cohesion here. They are sticking this the cohesion. So there's the cohesion, right? So that's a very important equation. The shear strength of soil is equal to cohesion plus friction. So that is the Mohr Coulomb strength envelope. Okay, this is very important failure criteria. The soil strength, the shear strength of soil, right, consists of two parts: cohesion, C, plus the internal friction, sigma dash is the normal stress times the tangent phi, right? The coefficient of friction. So you got this very clear and neat diagram for the Mohr-Coulomb relationship for the shear strength of soil, because S is equal to C plus sigma dash tangent phi, right? This is a straight line equation. Remember, y is equals to C plus x times m, right? That's a straight line equation. So m is the gradient, right? So the gradient m equal tangent phi. And here is the, x, and that's y. So y is equal to mx plus c, right? C is the cohesion, the intercept. It's a straight line equation. Let's recap, right? When you look at this shear strength against the normal stress, shear strength, and that is the normal stress, normal stress, and C is the cohesion, and here the angle of internal friction. So here's the angle of internal friction, okay? It's the friction between the soil particles, okay? And then you have, the cohesion here, sticky rice, right? Very sticky particles. But sometimes under the heavy rainstorm, the cohesion could be lost. In other words, the soil could be suddenly losing all its cohesion. So the whole soil mass could be sliding down, just like the unstable slope. Under the very heavy rainstorms, many slopes are prone to fail, right? Just because they are losing the cohesion. So the shear strength has lost some part of it. So are you listening? Are you are you still listening? Do you all understand what I was talking? Not quite. Which part is most difficult to you? You don't know? Which part is more difficult? Now, I'm going to demonstrate the use of this Mohr Coulomb envelope. Now, I hope my explanation will help you to understand the meaning of this criteria, okay? So please pay attention. It's a very important topic. For example, you have this soil element. The horizontal stress is 20. And then you apply, say, 40. Now, for this element, right, here, twenty, 0, right, for this point, say, that's A, is the B, so that is the point A. What about for point B? 40, 0, right? That's point B. So what's the Mohr circle? Is that clear? Now, will the soil fail? Well, it depends on here. So that is the shear stress. That's the normal stress. So the shear strength, C plus what? Sigma tangent phi, right? Now suppose that is C, right? Say is 80, right? And that is, say, 30 degrees, right? Now, what's the conclusion here? Because the Mohr circle here drawn here is well below this Mohr Coulomb failure envelope. Because it's well below this failure envelope, this straight line is the limiting strength of the soil. If anything below, so the material will not fail. So no failure of soil, right? Now, what about if this element, again, 20, 20, but the stress now is increased to 100. Okay, now 100. So again here, so that is A, sorry, so A here, and what about B here? B here, B dash here. So that's B, right? B dash, because here's 100, 0, right? So we draw the Mohr circle. Will this soil fail? Again, no failure. Why? Because it's still below the Mohr's Coulomb failure envelope, right? What about this element? $200. Again, it's 20. So that's A, but now is B double dash, right? So if that is, 100, now that is 200, 0, right? So if you draw the Mohr circle, what will happen? That's B dash. So will the soil fail? Soil fails. Because it's closing this failure envelope. Now, it looks very sensible, right? First of all, under the confining stress, the horizontal stress, 20. When you increase the vertical stress from 40 to 100 and then to 200, the specimen finally fail. Now you may imagine or ask why the vertical stress will be increased. Let's suppose before a building foundation is built, the stress at a certain depth below the ground is subjected to 40, right? 40 kPa, right? The vertical stress there is 40 kPa. But after you have built the foundation, the weight of the superstructure is very heavy, right? The vertical stress now comes to 200. So that exceeds, right, the shear strength of the soil at that depth. So the more Coulomb failure envelope tells us the soil can no longer take that sort of foundation loading. So the soil will fail. Okay. So does it look very sensible now? Well, for this slide, I'm not going to repeat, right, what's the cohesion and the angle internal flexion and so on. Right? The inclination of plane of failure caused by shear. As you can see from this diagram, here, the cohesion, right? The cohesion. So the cohesion and the friction angle. Okay. Now, if there's a state of stress, sigma 1, sigma 1, sigma 1, and sigma 3, and the sigma 3. So if that pair of the stresses, for that pair of stresses, you draw a Mohr circle, which are just touching at the point D. The point D here. So can you work out the relationship between sigma 1, sigma 3 in terms of the cohesion and the angle of internal flexion? The result is here. Sigma 1 is a function of sigma D, sigma 3, C, and phi. In other words, for a specimen, if it is subjected to a sigma 3, we want to know if that is C and phi. The basic characteristic of this soil is C and phi. Now, can we work out how much will be the sigma 1? Sorry, sigma 1. by how much sigma 1 will be increased until the soil fail. In other words, for a certain depth below the ground surface, if we put up a building sigma 1, a very heavy loading sigma 1 there, and we want to calculate whether the soil at that depth will fail or not. So that is a very important foundation issue, right? A very critical design issue for a given sigma 3. And we know from the, from the site investigation, after we collect the soil sample from the ground deep below, and then we send all the soil specimen for the laboratory testing, and we got the C, the cohesion, and the angle internal friction phi. Now everything is ready, right? We know sigma 3, C, and phi. Then how much will be the sigma 1, the maximum value that can make the soil fail? If we know sigma 1 is by how much, then we should know how high should the building should be built for that given depth of soil. Now we can prove this equation. Okay. Now okay. Now that's R, the radius of Mohr circle. That's also be R, and that is sigma 3, and that's sigma 1. Okay. Now first of all, from this diagram, R is equals to, what's the length here? Sigma 1 minus sigma 3, right? So R is equal to sigma 1 minus sigma 3 divided by 2. Okay. And then we consider this consider this right angle triangle. This right angle triangle. What's this? This should be C over tangent phi, right? Because that is a right angle. So the whole length, consider the green triangle. Okay. So the hypotenuse, the diagonal, right, equals to what? Sine phi equals to R, right? That is the whole length, hypotenuse. Sine phi equal to R. So what is the length of the hypotenuse? Sorry. C over tangent phi plus what? That is sigma 3 plus 2R, right? So that is the hypotenuse. Sine phi equal to R. Okay. So you got this equation 1 and equation 2. Now putting equation 1, the R, right? Putting R into the equation 2 and use this compound angle formula. 45 degree plus phi over 2 equals to 1 plus sine phi over 1 minus sine phi. And then you will obtain the sigma 1 equal to sigma 3 tangent 45 degree plus phi over 2 plus 2c tangent 45 degree plus phi over 2. So it's a matter of mathematics, right, to prove this formula from the Mohr Coulomb envelope. And using some mathematics, right, and also compound angle formula, then you could obtain this equation. Of course, you need not remember this this equation. This equation will be given to you, right, as a part of the examination data. For the Mohr Coulomb envelope, it's important to know the C and phi, right? Now, you can collect the soil sample from site investigation. You spend a lot of money to do the borehole, to drill the holes into the ground, and then at various depths, you collect the soil samples from the underground, right, the borehole, and send to the lab, send all the soil sample for lab tests. And you can get very accurate measurement of the cohesion and angle internal friction. You could also do the in situ test. In other words, you perform the test directly in the construction site with the soil there. Right? You don't need to pick up any soil sample from the ground below and do the test directly over the site. Okay. Once you know the C and the phi, then you know C tangent phi, right? That is the, because you know the C and also you know the phi. So you establish that straight line, right? The Mohr Coulomb envelope. Example 2. It's required to evaluate the shear strength of the soil at a certain point on the horizontal plane, as shown in the figure below. And you got the strain parameters, right? So let's take a look for this example. Right? So that is the question asks you to calculate the stress at that point A. And also check the shear strength at the point A there. So you got, right, that's the ground surface. And then that is the groundwater table. And you have the bedrock here. So, and then you want to know the point A here. So gamma 1, 13 km per cubic meter, right? And here, and gamma equals 15 kN. And you got C equal to 10 kPa and phi 35 degrees. And here you got so 2.5 meters, and here's 4.5 meters, and this 1.5 meters. Now for the A, so the vertical stress, sigma point A, right? Sigma 13 times 2.5, right? Because you know the summation gamma H, right? So 13 times 2.5 here, right? And then plus what? 15 times 4.5, right? But that's the total stress, right? You know, you come up the point here, right? 2.5, 4.5 meters. So you got the total stress here. And you have minus the U, right? What's the U? You can see here. What's the pore water pressure below this groundwater level? So the unit weight of water, right? Unit weight of water times the depth. What's the depth of the water there? 4.5. Right? So equals to the effective stress. Remember, effective stress. Dash is the effective stress. Equal 55.9 kPa. Now check the shear strength at A. S equal to what? C plus sigma A tangent phi, right? So it's equal to what? So it's equal to, what's the C? C is 10, right? 10 plus sigma A dash tangent 35. So it gives you 49 kPa. Okay. Now for the above example, we have considered the shear strength of the soil at the point in the horizontal plane. In fact, we should need to examine the shear strength in the vertical plane too. What's that? We have talked about this, right? So we have evaluated the shear strength due to the vertical stress only. What about here? But usually in a site, there should also be horizontal stress. In other words, it's not as that simple. Right? In the previous example, we just work out the shear strength due to this, the sigma A equals to 53, 55.9 only. What about if there exists the horizontal stress here? Now that will affect the shear strength of this specimen, right? So you sometimes have to work out the horizontal stress. Now that is sometimes called the lateral earth pressure. Okay. Vertical pressure and horizontal pressure. Right? K is a ratio of horizontal stress to the vertical stress. It's called the lateral earth pressure coefficient. Now we will study quite a lot about this horizontal or lateral earth pressure in a separate chapter. Now for the example 3, you base on the data from the example 1, construct the shear string envelope or the same plot. Draw the Mohr circle for point, assuming that the principal stress act vertically and horizontally. In other words, we have not only the vertical stress, but also the horizontal stress. Now, here comes the solution. Right? The vertical stress, 55.9 kPa. And here you got the K value, 0.65. So you can work out the horizontal stress, sigma x. Sigma x is the horizontal stress. Right? In other words, in the previous example, 53.9 kPa here, and here you got 36.3, right? Okay, so you got the point here, and the point here, you draw a small circle here. It's well below the, the Mohr Coulomb failure envelope. So there should be no shear failure. Right? Now, this is an important note. In the soil mechanics world, we talk a lot about the compressive stress because the soil particles are always compressing each other because due to the gravity, right? So the soil are very heavily masses. So we seldom have tension developed in the soil. So the geotechnical engineer will use a lot of the stresses in the compressive nature. So that's why we take all those compressive stress as positive, right? Opposite to the steel and the concrete. Right? In the concrete and the steel studies, we often take the tension as positive. But here, for the foundation and geotechnical engineering, we take the compressive stress as positive. Right? Of course, in the same way, the shear stress in counterclockwise direction will also be deemed as positive. Okay, so I leave this slide to you. The shear failure will not occur at A. Now, in situ shear strain of soils. We have laboratory tests, but also the in situ tests. So you have the lab tests and also in situ tests. They are all very valuable information for the geotechnical engineer, learning about what's the soil behavior under the loading. Now there are several kinds of in situ test method, including first of all the shear weighing test, Now what's it? You can see here, right? That is the weight, the shear weight, and you rotate it. What will happen? The soil of a cylinder volume, that's H, the diameter D. So when you rotate it, when you rotate it, so there is the torque, right? The moment, right, which make the wing rotate, right, in a counterclockwise direction. So to balance it, there will be the shear stress, right, over this cylinder surface will be acting in a clockwise direction, in opposite to the applied torque, which is in counterclockwise direction, so that it will be in static equilibrium. So that is the shear stress. And here we call it cohesion, right? So the cohesion is equal to the shear stress developed on this surface of the cylinder. And also, if you look at the bottom, the bottom, here the bottom, right? Now there's also the shear stress developed, but of course in the center, right? So the maximum shear stress will appear at the outer surface, and close the center, the shear stress will be smaller, right? So if you use the calculus, right, and to analyze the shear stress which contribute to this torque, you can obtain this equation. Right? So I'm not going to derive it. Right? So over the site, when you measure the dimension of these vents, right? So DH are known, and you apply the torque. The torque is known, right? So from this equation, you can work out the cohesion of the soft clay in which you have inserted your vent. The units will be in terms of Newton meters. Please pay a small attention that sometimes the above equation overestimate the cohesion a bit, and you should apply a correction factor, which depends on the plasticity of the clay. Okay. Now, standard penetration test. Standard penetration test. SPT. Now, what's SPT? Okay, now suppose that is a ground surface. So it's the ground surface, right? And then that's, there's a hammer, 63.5 kg, and you drop a distance of 760 mm. So hit it. And then you got a sample tube, sampler tube to collect sample. Now it's a split type. So split type. So it can be separated easily into two pieces, right? And the soil particles and the soil sample will be collected, right? So when you drive this sampler, so when you hit the sampler tube with this 63.5 kg hammer, right, dropping at the height of 760, so eventually this sampler so that is the sampler, right? This sampler will go into this position, right? So it will penetrate at a certain distance. Now, so first of all, we come to that level and then hit it and then hit it. Now, for the last 300 mm penetration, we can't blows, numbers of blows, to give you a penetration. It's usually about 1000 mm. Okay. When you drive this sampler tube, right, go into 1 meter further below. For the last 300 mm penetration, what's the number of blows? That will drive this sampler tube into the final 300 mm. That's the end value. So this is called SPT values. Standard penetration test value. Okay, so here we go. The standard penetration N value is the number of counts, right, for the last 300 mm penetration. Harder the material, you need a higher number of counts, number of blows, right? So in other words, higher the N value, the soil material give you a greater resistance, a better soil. Now, also we not only for the 300 mm penetration, for each, right, 75 mm in one should be recorded. In other words, here you need the number of balls, right, and 0, 75, 150, 100 and 225, and then 300. So you need to record the number of blows, right, at every 75 millimeter at once until you come to the 300 mm. That's the N value. Now, what's the use of SCPT value, SPT values? You can see here the N value related to different relative density of sand. For N value 0.4, very loose, right? So the N value, so you need only 4 blows, right? That can give you 300 millimeter penetration. But for very dense, the number of blows could come greater than 50 blows, right? Before you can get 300 millimeter penetration. In the same regard, right, for the cohesive soil, cohesive soil, the previous slide for sand, here you the cohesive soil. Again, for very soft clay, you need only almost 1 blow, right? It can give you 300 millimeter penetration, so it's too soft, right? For very hard and stiff clay, right, you need number of blows could be greater than 30. Okay, that ends up our chapter 3, the shear strength of soil. So you are still there? Or already fallen into sleep? So can you understand the chapter 3? Slide 17, okay? Okay, what's the question? Now I can give you 5 minutes break, okay, before we step into the tutorial 1. After my discussion for several problems of tutorial 1, then you have to go over the whole assignment yourself, right? And then you should submit the assignment to me in the next Tuesday evening by email. Is that clear? Okay, let us take 5 minutes break.